Hello, I'd like to thank everybody for attending my presentation as part of the 2021 CLRA conference, the Alberta chapter virtual AGM, occurring February 24, 25. So I hope you enjoy all the talks while you're here. Today, my topic is surfactant-enhanced recovery of heavy separated phase petroleum hydrocarbons at a Superfund site in New York. So I'll be talking about the background about how LNAPL type contamination behave and what really affects their behavior. And then I'll be spending a bit more time than I normally do on this specific Superfund site. And then I think time's going to allow me to slip in one more about a site that has both LNAPL and DNAPL at a manufactured gas plant type site. So without further ado, let me get going. So these are just images showing, obviously, free phase in contact with contamination before and after, and that you are capable of actually treating those and increasing their availability for remediation. So part of a theme that I'll be talking about today. This PowerPoint, although it's our copyright, if someone would like a copy of it, my contact information is at the end. The conference organizers may be posting some of our presentations for you to review afterwards. So one or the other will be available, so don't be shy. An important factor when you're dealing with any type of remediation product is to understand its purity. So we've all heard of like industrial grade, commercial grade, maybe medical grade or research grade. The purity increases across those four that I've mentioned, as does cost usually, right? So when you're dealing with any kind of remediation product, make sure it's free of any impurities or byproducts of concern, or if there's constituents associated with it, that after the application that you actually make sure you monitor before and after, get your baseline, like if you're using a sodium permanganate or something, make sure that you don't have more sodium than you want pre to post while you're applying that, because you may solve your problem but have a lingering issue. So just be mindful of that. So an important thing that I'd like to raise regarding the Ivey line of products and our decontaminant product used for decontamination of like field equipment and things like that is we're free of PFOA, PFOS, 1,4-dioxins, dioxins, furans, PCBs, and have been tested and free of US EPA regulated compounds. And over time, if new contaminants of concern come along, we will test for those as well. And we've also developed a newer product that's actually designed to deal with PFAS. So if any fluorinated impacted sites, particularly those with a little bit of organic content, we're looking at trying to attenuate the remediation of those. So feel free to reach out to me. So when we're dealing with free product, we tend to think of them typically in extremes of it's a floater or it's a sinker, right? Well, it's not quite that simple. There's a lot of different densities to the different compounds. We don't typically go to a spill, oh, I have a pure benzene spill or I have a pure this spill. It's usually a mixture, like even gasoline's over 2,500 compounds. So when you're looking at these contaminants, yes, density will come into play, but also that contact between the water and the contaminant will come into play and its behavior. It's called interfacial tension. So if it doesn't dissolve, it's either going to come together and form globules or an actual measurable NAPL phase. It'll also absorb to the soils. And the finer the grain of the soils, the more surface area there is for absorption. So you can be mindful of that. So when you have this contact taking place, as you can see between these free product floating and sinking layers, there's interfacial tension also in play. The surface tension of water is 73 dynes, while the surface tension of most contaminants, whether petroleum hydrocarbons or chlorinated solvents, is in the low 20s. So a big difference. And that can affect movement of these or your intentional movement or interaction with these when you're treating soils and groundwater. So we know when we have a spill, they're usually accidental. That happens, above ground, below ground stinks, pipeline spills, truck rollovers, the list goes on. Because of that, if the compounds are relatively light, they're volatile. So you may have vapors going to the air, or if they get in the ground, vapor intrusion into a building. If they're light compounds, they'll come in contact with the water table, and the movement of that water table and the depth of that water table will probably slow it down, and it'll tend to follow that pathway. If they're a little more dense or intermediate density, they'll keep going down. If they're particularly dense, they'll keep going down until they hit some kind of a confining layer. Could be bedrock, could be a really tight, stiff geology, and then it'll migrate from there, typically following the groundwater flow, okay? So this is not uncommon to us, but it happens at a lot of sites. Now, when you do have free product, this is an interesting baler shot from a site in that we have LNAPLs in this baler, we have some DNAPL in this baler, and we have some intermediate compounds. This is from a manufactured gas plant. So there's a whole mishmash of different compounds of varying densities that are in there. So when you're treating it, it's not as simple as I got a floater or a sinker. Even in gasoline, you've got a lot of different densities of compounds. So when you're looking at that, when you do have contamination in there, whether it's sorbed vapors, sorbed oils, or free phase, and it's coming in contact with water, again, the interfacial tension will be a factor. So if the trapped oils, as it were, or solvents come in contact with water, they can't push past this. They get kind of trapped. And they slowly dissolve in, doing a process called back diffusion, causing contamination of the groundwater. But if the groundwater is moving, or you're trying to move the groundwater, it'll kind of hit it just like a pier below a bridge in the river. It'll hit it and it'll move around it because it can't get through it, and often follow a different pathway, leaving that contamination isolated and in some cases untreated. So you'd be a little bit mindful of that. And when it kind of gets trapped there, we call that pathway interference, which can affect physical, chemical, and biological treatment. So that interfacial tension's a really important factor for vapors, which get sorbed, as do the contaminants, and then there's globules and free phase. They're all, in certain cases, going to be present on sites. So a simple way of looking at this is the surface tension of water is 73 dynes. We know if you do a belly flop on water, it hurts. If you did a belly flop on ethanol, which is in beer and wine, you'd probably find it doesn't sting your skin because it's down in the low 20s, which is very similar to a lot of contaminants. So because of that, it really can't push back there, and it gets like a cork in a bottle, it gets held. So I talked before about things that have a lot of different densities. So for example, in this illustration, what I'm showing you is a vial with a lot of different liquids in it. So for example, you have a ping pong ball floating on lamp oil. And that lamp oil is on top of rubbing alcohol, and we got a soda cap floating in there, which is on top of vegetable oil. We have a bead. Then there's a layer of water, a cherry tomato with kind of intermediate density. And then we have soap, a layer of dye, milk, maple syrup, a popcorn kernel, which we kind of think is a bit heavy, but it's not super, super heavy. Heavy enough to be down here pretty low. Then we have corn syrup, honey, and there's a brass bolt at the bottom. So what this makes us realize is that there's a lot of different densities of things. And if you ever gone to a bar where they pour you a drink and there's multiple layers, the person behind the bar is playing with the density of those liquids. So don't go thinking that things are going to be absolute floaters or sinkers. Sometimes their behavior and movement will be affected by different factors, not just density or solubility. So when they do come in contact with water, interfacial tension will be something to consider. So there we are, just showing free phase contamination. That's actually frac sand for upstream oil and gas. That's actually drill cuttings. And there's just showing somebody holding a palm of very impacted soil from an oil and gas region. So when we're dealing with contamination, the contamination is often because it's not very soluble. It's going to be in a sorb phase, or as globules, or as an apple phase. Trapped in the pore space, so you get enough that sometimes you'll see a floating product or a sinking product if there's an appreciable amount of it. But if you want to remediate that by any physical, chemical, biological method, you need to make that more available. So sometimes we'll apply multi-phase extraction, which can help tug those off and you can recover it, but that doesn't always work very well. Anyway, so if it's not in that available form, you're going to have some challenges trying to remediate that. And I like to use this analogy that goes back to a quote from 2005 talking about what they've been considering a concern for over a decade when it comes to remediating contaminated sites relative to desorption. It's going to focus on bioremediation, but it's not limited to that. It includes physical and chemical processes. During the past decade, much discussion has centered on the unavailability of sorb compounds to soil microorganisms. It's now generally assumed that desorption diffusion of bound contaminants to the aqueous phase is required for microbial degradation. And by the way, the heavier the compounds, the more they sorb, okay? So we tend to see those mid-range to heavier compounds creating a lot of challenges for physical, chemical, and biological remediation. But if you could desorb those, you can overcome that challenge and improve those processes, because they are, in the case of biological degradation, very biodegradable. Lots of good energy in there for the contaminants. So again, sorption or free phase formation will limit the availability for things like multi-phase extraction, pump and treatment, soil washing. Or if you're doing biological anaerobic or aerobic or facultative treatment systems, it can limit the availability to the bacteria. So you want to make sure those microorganisms have access. If you're doing chemical processes to even things like oxidation, reduction, electrokinetics, the availability for that can be limited. And so you just something to think about. If you can do something, if what you're applying is working, stick with it. But if you need to enhance it or nudge it along, think about what I'm going to be talking about today. So again, sorption, globule, and apple formation limits availability of contaminants. So we've come up with some ways to overcome that. So the mechanism for how Ivey works, if we look at this mechanism drawing that I'm showing here, we have a layer of sorb contamination. This could also represent the floating or sinking NAPL phase. And Ivey works at it at a molecular level. Okay, what I designed was I understood that the various contaminants have different functional groups. I jokingly say something has an ear, a nose, an arm, a hand, a foot. So I just want to interact with that portion of the molecule, not the whole thing like most surfactants. And it gives me a bit of predictability and allows me to work at a lower concentration, right? So that's what I want to do is work below the critical micelle concentration. An analogy for that is imagine you're the oil droplet and a ping pong ball's a surfactant. To create a micelle, I have to cover you with 500 ping pong balls. Now you're enveloped by it. That's not what I wanted to have happen. So by not emulsifying you, I can target it, use it at a lower concentration. Plus, by not forming an emulsion, you can treat the wastewater through an oil water separator, and it's still available for activated carbon, Mycelex, bioreactors, membrane separation, the list goes on, and still meet your discharge permit for that water. Right there, I'm showing you what a typical micelle does. Well, when it's completely encapsulated, it's not really completely physically, chemically, or biologically available. Plus, it's emulsified. Try treating that through an oil water separator. Try to treat that through activated carbon or other methods you use. You'll find it'll be very difficult when it's emulsified. So that's how typically 99% of surfactants work. We didn't want to do that. So because of that selectivity, what we want to do, we came up with different formulations for clients to apply, whether it's a gasoline spill, a diesel spill, PAHs, chlorinated solvents, the list goes on, even including the new PFAS salt product that we came up for dealing with fluorinated compounds. And then we have things that we've developed specifically to help enhance the decontamination of field equipment. So you're going out, you water level meters, DO meters, product probes, and you want to decontaminate between the wells, we can actually meet and exceed the ASTM standard for that. And our products, again, are free of unwanted, like things like 1,4-dioxin, which are actually in some decontamination products, so be careful. And again, because of the way we work, we can be diluted in water. So imagine you had 1 drum of our concentrated product, not 50 drums of diluted. So 1 drum can actually make the equivalent of about 50 drums of injectable fluid. So that's why we send it as a concentrate, but allows you to dilute that with your clean water you have on site to then apply it. So it's very sustainable to even ship. It's biodegradable and it's non-hazardous. This is an interesting image. It actually shows a droplet of water sitting on sand. Shouldn't that just go into the sand? It's water. What's going on? It seems kind of odd. Well, today what I'm going to tell you is that we often think of water as being H2O. Well, it is and it isn't. What do I mean by that? I'll try to explain it to you. So what I like to say is what you see at the macroscopic level speaks to what's happening at the microscopic or at the atomic level. What's going on in here? Why is that water beating this way? And why does it look like almost like a perfect, orb in the sense of its structure? Well, it comes down to what's in there. So we know that in the upper right-hand corner of the periodic table up there, things are more electronegative, so we put a delta negative on it. Things up where the hydrogens, sodium, calcium, they're electropositive, so we put a delta positive. And what's that look like? It looks like a magnet. Interesting. Now, typically in high school or early chemistry courses, we've been told about how water has interaction between the oxygen and the hydrogen, the neighboring molecule, doing something called hydrogen bonding. Explains why you do a belly flop in water and it hurts. But it doesn't stop there. It actually reaches out to its neighbors in all 3 dimensions, and then they grab onto their neighbors and grab onto their neighbors and their neighbors. So you don't really want to think of water so much as just simply H2O, because it really isn't that. Even in vapors coming off of the kettle, if you're going to make some tea, it's actually a 3-dimensional cluster. So if you want to take a minute, put that into your Google search after this presentation and read what you'll find out about it. This has been going on for decades. We've been studying this. It's actually quite important, even within our cells and our ability to deal with things such as shunting different ions in and out of cells because of this capacity. But this is what you're pushing and pulling. So the finer the grain, the geology, it's like instead of pushing a mouse around, you're pushing an elephant around. So that's why your K value drops in finer grain geology. But not only did I realize I had to make something that wasn't miscible in water miscible, so it's more available physically, chemically, biologically, I also had to change the behavior of water. So I found that I could also change water from being large clusters to small clusters, or from 73 dynes down to the 20s or 30s. And this actually makes the cluster smaller. So if we're dealing with contamination that's trapped inside pore spaces, you need to have access to those areas. You need to have delivery to those areas to do whatever you're doing physically, chemically, biologically. If you don't, you're not going to have much of an effect. So I realized if I could change the behavior of water, I could improve access and regress. The following slide is going to kind of illustrate that. So here's that same pore space with maybe some sorbed vapors, maybe some sorbed contaminants, or some of that NAPL phase. And by changing the size of these water clusters, we start to get access. We can get those Ivey cell molecules in there to start doing some of that work about improving the availability, physically, chemically, biologically, so that they're more available through the mechanism I described earlier. And by being more available, your physical, chemical, biological process, or combinations thereof, works better. You need access and regress into those spaces. If you don't, Your site may appear to be cleaned up, and all of a sudden, whoa, what happened? The contamination came back. Or, oh, I thought we cleaned up the free product, it came back. See this all the time. So this allows us to deal with that, okay? Very important consideration. So when we look at surface tension again, we talked about water having 73 dynes, most contaminants having around low 20s of dynes. So imagine them coming together. Those contaminants really can't push past the water very much, so it's being contained by interfacial tension. There's also the cohesive forces between the two that want them to be hanging out with their buddies as they do. So what we can do is we can introduce the Ivey sol, which is miscible in water, but it's also miscible in the contaminants, and has the ability to take those contaminants, and by making them miscible, allows you to then get these two phases to come together, and that limitation of interfacial tension is overcome. As a result, increasing the availability of these contaminants for those methods that you're applying. So this is really critical. Here's an example of interfacial tension of some floating product. L-napple or D-napple on the right, and we're making that more available. That's all we're trying to do. By the way, we're not a pump and treatment system or multi-phase system or bacteria or chemical oxidizing or reducing or any of those other electrokinetics. You have to have those systems if you're doing that. But if you need enhancement, we can help. So when we're talking about applications, the two most common things that we do is we do what we refer to as a push-pull. We put in vertical wells inside that area of your plume. They're screened across your zone of contamination. And when your water table goes up and down, by the way, if there's any free phase, it's going to make a smearing of contamination. So make sure you cover that. So your investigations to determine it. And then other cases where we're not just treating around these wells, we'll put some injection wells on one side, has some pumping wells there, and then we'll sweep and wash across it. And I'll show some animations of this later. So push, pull, and sweep are our two most common methods that we use. So now what I'm going to show you are a series of three-dimensional animations with a description. I've got a technical person assisting with me to make sure these click on and work properly. So let's go to the first one. In this one here, you'll go into your site and you'll do your investigation for vapor, soil, groundwater contamination, and characterize where that plume is. Based on that information, we can then model, say, let's say in this case, we're using vertical wells or angled wells, where we need to put them. They're typically about 100 millimeters or 4 inches in diameter, screened across that zone of contamination. We inject the required Ivey sol at the proper dosage into there. You can often do it by gravity feed. You can use pressure if you like. It's less often for us. You can cause mounding by just doing the gravity feed or putting a packer in there. You target your zone of contamination. It goes out, and typically a residence time of 24 to 40 hours before we extract. Well, that Ivey sol's in there making contact with absorbed vapors or absorbed contaminants or those globules of napple. It's making that miscible so that you can recover that mass. And this is basically like a sequential extraction. So over a limited number of these, you can actually realize a really quick reduction in contamination. And if you take a number of time-based samples, you can see this happening pretty quickly. So another scenario here is where we have to establish a hydraulic control. It's like, 'cause maybe the plume's moving. Maybe it's going to some water wells, a wetlands, or maybe a nearby waterway, what have you. You want to stop that. So you establish hydraulic control on the site. And then in the vicinity of that well, which is usually positioned, there could be multiple of these, but this is a 5-spot pattern. Around that pumping well, you install a few injection wells. And these injection wells, when you injected them, are obviously injecting into a certain specific layer in the geology where the contamination is. And then what happens then is, by pumping at the central well, it nudges that Ivey sol you've put through that impacted geology where it starts working on those contaminants, making them miscible, where you realize that mass at the central well. And by taking time-based samples, you can see that happening in real time, okay? So it's another process. The third one I'm going to show you right now is, imagine you have a site where the contamination's gone under the building. Maybe it's near a pipeline or a fiber optic line or under a street or highway. We've had to deal with these. In those cases, you really can't go drilling out in those areas unless you want to rupture the pipeline or have traffic hit you or something like that, jokingly. So on one side, you'll put a series of injection wells. On the other side, you'll have some pumping wells. And then what you're going to do in this scenario is you're going to inject the injection wells, and in the subsurface, it's going to basically have the Ivey sol pull through the plume of contamination and realized at those pumping wells at the other side. And that way, it allows you to treat under that building, under that pipeline, or what have you. So getting to the case study, this is the Superfund site in New York City, which is a really interesting site, which I'll talk to you about some of the characteristics of it. It's surfactant-enhanced recovery of separated phase hydrocarbons at the Sunnyside Yard, New York City. It's a Superfund site, as I said. So here's a little bit of the story about that site. We went from a bench scale study to pilot to full-scale application. And as we do on a number of our sites, the clients, depending upon how sensitive the site is, litigious it is, Superfund sites are they're quite a sensitive site with a lot of eyes on them. We can take samples from clients and go into our lab and do bench scale studies under controlled conditions. We can receive samples not only domestically, we can receive foreign samples that can come into us under import permit. And working with our local labs, we can then take those, and they often send us soil samples, free product, even the groundwater from the site. If they don't send us the groundwater from the site, we'll obviously use water provided by the lab. And then we can perform testing on that. If, for example, the soils, we'll take their soils in this case, there's a person mixing it physically, a bunch of several kilograms of soil in a 9-liter stainless steel bowl, so it's well broken up, there's no clumping. We have it exposed. And then we can put that amongst all the jars of soil that we're going to be using during testing. We know the weight of every single individual jar, and by indirect measurement, we can determine how much soil we have in there, and then we can actually do the analysis to determine what absolute mass removal we achieved. All the testing in this case, because it was a Superfund site, was done in triplicate, not single tests, which are still effective, but this one required triplicate testing. And there it just shows not only weighing things, we're treating it, and once the soil's washed, you can put it on some paper towel to air dry in the fume hood, and then put it in the jars for subsequent analysis. And as you can see here, a lot of jars there because everything's being done in triplicate. Well, the same thing happens with our clients when they give us free phase. In this case, we're actually using their groundwater into a 4-liter beaker. In this case, we're using about 2,500 mils of the groundwater, and then we put about 100 mils of free phase on it, and we put a magnetic stir bar on the bottom, but we're only turning at the setting 3 of 10. So it's moving, but not so quickly to cause, shall we say, turbulent action or stirring. You won't see much movement on the surface at all of this liquid. In this case, we're doing 3 of these to establish baseline. How much that free product's getting in the groundwater? So we sample that and we get that value. Then we try 3 different dosages of the Ivey cell to see how much of that mass we can transfer in the aqueous phase for recovery by, in this case, our multi-phase extraction system. And then what we do is after we do that test, we use peristaltic pumps, as you're seeing here, for low flow sampling of the product into our jars for analysis. And this just speaks to the fact that we're always generating extra soil or other waste that the lab will manage for us. And then we are submitting our samples into the lab. So in this case, there's a Sunnyside yard. We had a very small area with a multi-phase extraction system to work on. There were 6 major impacted areas called operational units. We're in operational unit number 3. This site was a bit challenging, and there it is, showing in that little circle. So this site was challenged that it had some PCBs in the soils, but it had these heavy hydrocarbons that were causing the measurable NAPL. So our goal was to get that NAPL out, but we sure during our bench scale testing, by 3 orders of magnitude, we were liberating the petroleum hydrocarbons, not liberating the PCBs, which was pretty critical. So here just shows the multi-phase extraction system they had set up across the site. There's an air photo. That linear building you're seeing up and down the bottom of the photo is the treatment system. So what they did, and this just shows you where the treatment system's actually sitting, where they actually wanted to develop a new high-speed train facility. Interesting. So they had to do this and clean it up before they would get actually approval to do it. Here shows their cumulative mass recovery through the multi-phase extraction system. And the key part was 83% of that mass that recovered over these years of operation happened in the first 5 months. So it got what was readily available. It was that stuff that was absorbed or stuck in those pore spaces that we were there to help them get out. I explained how the Ivey Sol technology works earlier, so I won't spend much time on that, but you can see that inset photo of what we were trying to achieve. Make that more available for remediation so that they could recover it and treat it and meet their discharge permits at the site, as these illustrations again show. Moving really quickly, they gave us 8 wells that we treated over a 1-week period. There's actually an illustration of what they've since redeveloped. That was the architect's drawing, but it's actually been done now. We did bench scale testing, as I talked to you about. We did the pilot scale over 1 week at the site. We even have some field test kits to monitor where the surfactants are. There's before, and there's even traces of surfactant coming through, like in a sweep, so we can use this as a nice way to see what's happening. Here's the before and after thickness of the free phase at the site. And what I'd like to show people as another example is this is the mass removal that we realized in that 1 week. Realizing an average of 81% mass removal was realized. Not bad. And then the nice part about that, as I showed in the previous slide, we did this in late October. By July of the following year, there was no change in what we had removed. There was no rebound, so it held consistent. Then we went to full scale, which was great. I'm happy to share with you that in my conclusionary slide on this one, the separated phase hydrocarbons were enhanced by the Ivey Cell application, which paired very well with their multi-phase extraction system. The free product was not observed in the extraction groundwater. We got it kind of in slowly. We did not hinder their wastewater treatment system. Whatever mass removal we realized was realized within the first 24 hours, and it held consistent. They tried high concentration, low concentration, and it pretty much showed them about a 1 to 40, 1 to 50 dilution was the answer, so that they found it was cost effective and sustainable. It was a really effective way for them to treat that operational unit number 3. And they liked that in these 3 applications, we caused a really significant mass reduction on some of those challenging wells. And as I said before, they went to full scale. And at full scale, they literally cleaned the site up in months, and it's been since redeveloped. So I'd like to thank everybody for attending my presentation. I hope you really enjoy the CLRA conference. And for any of those that are interested in speaking with me or asking any questions about the presentation I gave, here's my contact information. I'll be hanging around for the question and answer period. And thank you very much, and be safe out there. Bye now.